All right, hello lovely humans, welcome to part 2 of the time-independent Schrodinger equation. We are going to dive into the nitty-gritty details of the mathematics. Woohoo! Yay! Okay, so I'm skipping a few steps to get to this point, including the physicist's first line of attack, as stated by Griffiths in the quantum mechanics textbook, of using separation of variables on the full Schrodinger equation. And basically what that means is that we are assuming that the general wave function, which is a function of space and time, can be written as a product of two separate solutions. One wave function which is a product of space only, and one which is a product or dependent on time only. And so in doing that, we actually can get out the time-independent Schrodinger equation, which has these full derivatives and is much easier to solve. Good. The other thing about this is that it turns out that when we apply normalization, aka when we solve for the probability density and we ensure that when we add up over all of space and time from negative infinity to positive infinity of space and time, it actually turns out that this is a reasonable assumption to make. And we can also think about this as the wave function being a series of stationary states. In other words, the wave function that we get out will not really change over time. And the other thing that is nice about this approach, besides that it makes the math a lot easier, is that it actually allows us to solve for the wave function as a function of space, and then we can add in how the wave function changes over time and kind of and analyze the pieces separately. But we're going to start simply and just use this particle in an infinite box to start a foundational understanding of what the Schrodinger wave equation is and how we actually go about solving it. It's a pretty complex equation, but we can handle it if we break it down into simpler pieces. And that's where this problem is really beautiful. Even though it's not a real world problem, there's, very unlikely scenario that there is an infinite amount of energy required to get out of a certain situation, hopefully. But it does give us some really useful results. So first of all, what does it actually mean how do we define this problem in terms of mathematics? I drew it by saying, okay, our box is of length A, so our particle can move along the x-axis from 0 to A. And when it reaches the box, inside the box is kind of free to move. In other words, the potential energy is 0 inside the box. But when it hits the ends of the box, it would require an infinite amount of energy, so basically it just bounces off and it's like, oh, too lazy for that. So the mathematical way of representing that is that our potential energy is a function of space, and it is 0 inside the box, or basically where x is between 0 and A, and it is infinite else. The other thing that we want to say is that the wave function outside of the box is wave function of x equals 0 outside. So these are basically our boundary conditions. And so once we set these, I'm going to erase that so I have some more space. Once we set those, then we can tackle the time-independent Schrodinger equation. All right, here we go. So I'm going to write it negative h bar squared over 2m full derivative of our wave function, which is a function of x only, which is why we can write the full derivative with respect to x squared. And then we have 0 potential energy inside of the box, so that goes to 0, makes our lives easier, equals the total energy of the particle, which we don't know yet. So we're using this E to represent that, times the wave function. Okay, so now to make this easier on myself, I want to get this piece by itself and write d squared of our wave function, dx squared equals negative e times 2m divided by h bar squared lambda of x. Oh, hey. So this is our old friend, the simple harmonic oscillator. Woohoo! Where that would just be written like that. And so in this case, we have k, we can define to be the square root of 2me over h. Whoopsies. The square root only applies to the top because h bar is squared. Oh no, but it would just be regular h bar. Okay, so there we go. The square root of 2me over h. So in this case, I'm just picking k so that it makes this look like the simple harmonic oscillator equation, because that I don't have to solve. Other peeps have solved it before me, and by peeps I mean mathematicians. So the general formula for the solution to simple harmonic oscillator looks like this, where we have a constant a times sine of kx plus a constant b times cosine of kx. Okay, so now we have a general form for our wave equation, but we have no idea what a, b, or really we don't really know what k is. Okay, so we defined it up here, but we don't know what the energy is. So we have to narrow down, we have to use what we do know to try and get a better understanding of these unknowns. And the first thing that we can do is apply our boundary conditions. So I am going to erase this. We're going to keep that for now. So our first boundary condition, which is the easier one to apply, is that when x equals 0, or I should say at x equals 0, our wave equation equals 0. So we plug that into this formula and we get a times sine of 0 plus b times cosine of 0. The sine of 0 goes to 0, cosine of 0 goes to 1, and we're left with b times 1 equals 0. Oh, look at that! We got to cross out that. So this whole term goes to 0 because b equals 0 for our boundary conditions to hold true. And then we apply our second boundary condition at x equals a. The wave function also has to equal 0. So now we have our wave function at a equals capital A, which is an unknown constant, times sine of ka equals 0. So for this to be true, either our constant a can equal 0, or this sine term goes to 0. So if we pick this, it was kind of pointless to do all of this work because we get a solution that is called trivial, or basically it's not very helpful. So we're going to ignore this and assume that it's the sine that goes to 0 because we're trying to get some useful information here. So in order for sine of ka to equal 0, the term on the inside, ka, must equal it either must equal 0 or some integer multiple of pi. In other words, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. And the reason is because sine of 0 equals 0, sine of pi equals 0, sine of negative pi equals 0. So all of these solutions would work for our equation. And so what we do is we say, okay, well now we actually have an equation for k. So k equals n pi over a, where n equals 1, 2, 3, etc. I ignored the 0 term because, again, that's one of those trivial solutions that doesn't really help us or give us any useful information. And I picked only the positive integers because of the energy term, which we'll see in a second. So now we know what k is in terms of things that we have defined in our scenario. So a is just the length of the box. Technically, we know a, even though we haven't assigned an actual number to it. Pi is just a constant, and n is an integer number that can be anywhere from 1, 2, 3, all the way up to positive infinity, but we technically know what n is. So now let's solve for e. And when we do that, we get e equals k h bar, both of those are squared, divided by 2m. And then we plug in this equation for k. So we get n squared pi squared h bar squared over 2a squared m. So this is really interesting and where quantum mechanics is truly bizarre and different than classical mechanics. Because what this is saying is that the energy that our particle can have can only be certain amounts of energy. In other words, it's not continuous. So that's very, very different because in classical mechanics, would be like, I can take a ball and throw it at any height between the ground and my hand and everything in between. I'm not limited to like rungs on a ladder. But this is literally saying that instead of being able to continuously increase the height of my ball to give it more potential energy, my particle has to take on specific values of energy. So that would be like if I were required to climb up a ladder and throw the ball at specific heights. And the different energy states are actually given by this integer number n. So I think I called it the fundamental state. I was thinking of sound, but n equals 1 is the ground state. It's the lowest allowable energy state for our particle. And so as you increase n, you give more energy to the particle, or aka the particle has more energy. I don't know if it's us that's giving the particle more energy. But this is really, really interesting because our energy is quantized. What? Super cool. Okay, so the one thing that we have left to do, we have an equation for the energy of the particle, which is soups bizarre. And we know what k is, but we still don't know what this coefficient out front is, what this a term is. And this is where normalization comes in handy. So I'm going to erase this to give us more space. I don't need that equation anymore. I am going to need k equals n pi over a, with n equals 1, 2, 3. Wow. There we go. And then I'm going to erase that there. Okay, so with normalization, so again, what this equation, this normalization equation means is that the probability of finding the particle somewhere throughout all of space and time has to be certain. It has to be 100% or 1. And so if I were to plug in this equation, in this case, my particle, the wave function of my particle, the probability density of my particle can only be inside the box. So I don't need to integrate from negative infinity to infinity. I only need to integrate over the box from 0 to a. And then I plug in this equation for the basically the complex conjugate of my wave function. And I get a squared times sine squared of n pi x over a dx. And since this isn't an integral video, this is a Schrodinger wave equation video, I'm going to be like equals dot dot dot, and then you get a squared times a over 2 equals 1, because this equation has to equal 1. So now I can solve for a. Yay! So a equals root 2 over a, and because we're most interested in the magnitude of a or the size of a, its phase doesn't really matter, I can pick the positive root, woohoo, to make our lives easier. And now, oh boom, we have an equation, root 2 over a, and I guess here I could plug in what k is, n pi x over a. Boom! All right. Like the math bosses that we are. Okay, so that is how we get the infinite set of solutions to this simplistic example. And now I get to look at my notes, and we are going to talk about some of the implications of this solution. So in addition to getting infinite solutions and quantized energy, super weird, we also end up with solutions that alternate between even and odd functions with respect to the center of the box. And so hopefully you watched the first video, and that is where we covered kind of the alternating even and odd functions. The other thing is that each successive state, aka as we increase n by 1, each of those successive states has one additional node. And here I have to correct myself. In the last video, I mentioned that the end points of the box were nodes. Technically, they're not. My bad. But the nodes are points at which the wave function equals 0. And apparently it only counts inside the box. Should have known better. Okay, so the other thing is that our solutions are mutually orthogonal. In other words, if we were to multiply them together, and I'm going to use a complex conjugate because I'm going to use good notation. So don't worry too much about this if you're like, what does that mean? Another way of phrasing this is that our functions, our solutions, are orthonormal, aka if you multiply them together, two different solutions, so m is not equal to n, I need to specify that, not equal to n, then they equal 0. And if you multiply them together and you sum them up for all of space and time, I guess, they equal 0. And this is going to be really helpful later on when we're doing more complex problems. It allows us to solve some tricky things by exploiting this property. The other thing that I should mention is that this set of solutions for the wave function, represent a complete set of solutions. In other words, we can write a function, we can write any function as a linear combination of these equations. And so if you've seen some of my other videos, you might recognize this. So from n equals 1, wait, I probably should, yeah, that's fine. Equals 1, Cn. Oh, look at that, it looks like a Fourier series. That's pretty much what it is. And again, this is gonna be super useful later on because we were able to use a simple scenario that allowed us to make some assumptions and solve this challenging problem. And now that we have a solution, we can use this property, this linear combination, where Cn is just a constant, and we can use this to apply it to harder problems. And then again, that in combination with the fact that our solutions are orthonormal, it'll allow us to solve harder problems in a way that's a lot easier than dealing with a second order differential equation, especially when our potential energy gets a lot more complicated. Okay, so I'm gonna leave it there for now. Please let me know if you have any questions about the conceptual understanding of what these equations mean. It's really helpful to actually go and plot them, so I would really recommend doing that. And plot the probability density too, because that's really where the meaning of the wave function comes into play, something that we can wrap our heads around. So let me know if you have any questions about the conceptual understanding or about the mathematics that we ran through. I totally skipped over the integral stuff because I wanted to keep this at a reasonable length. So if you're like totally lost about that, happy to provide more details. All right, thank you for watching, and we'll see you next time where we tackle a slightly harder problem with the Schrodinger wave equation. Yay! All right, bye!